Hey, welcome to another video. So in this video, we're going to try to find all the zeros, all the solutions to a polynomial, including some complex ones. So I'm going to walk you through about 6 examples. For the first two, we're given a complex solution. We find the rest of them, including real solutions. Then we're going to remember to not forget about factoring. And then lastly, we're going to start from scratch and find every single solution that we can. I'm going to show you exactly how to go through and do that from a polynomial. So I do want to admit that the first two examples are sort of contrived because I'm giving you a complex solution first. And while that is possible to do, it's not very likely. So I'm going to admit that the first two are kind of like, would these really happen? Probably not. We'd probably find real zeros first if there are any. But if there aren't any, then we're left with the idea of find a complex solution first. The reason why I'm going through these is because this is going to teach you how to do long division of polynomials without a linear factor, with a quadratic factor, an irreducible quadratic factor. And that can be an important concept as you get into something like Calculus 2 when we do some of the partial decomposition of fractions. Right before that, you learn how to do long division. And so we're going to be doing that sort of as a preface. And if you happen to get a problem like this, where you do have a complex zero, how to structure it. So we're going to start right away with this example, x cubed minus 4x squared plus 4x minus 16. And I'm going to tell you that it has a zero of 2i, or a solution, a complex solution of 2i. And that's a complex solution. Of course, it'd be 0 plus 2i. That would be the real part plus the imaginary part. And we're going to find the rest of them. So here's a couple things to refresh your memory about polynomials. If you have a degree 3, then there are going to be exactly 3 solutions to that. Now, some might be repeated, but there will be 3 solutions. Given 1, we should be able to find the other 2. In complex numbers, this is always true. So if we have a degree 3 for a polynomial, you are going to have 3 solutions. So here's the idea for all we're going to do today. Number 1, we're going to find a 0. If they give you one, awesome. If not, we're probably going to have to fall back on the rational zeros theorem to find our own zeros. Number 2, we're going to create a factor. If you have a real 0, well, then you're going to create a linear factor and you're going to use synthetic division, and that's really quick. If you don't have a real 0, if you have a complex 0, then the thought process is, we learned in the last video, if you have a complex 0, they always come in complex conjugate pairs. They come in pairs. So we're going to take a pair of zeros, get a pair of factors, distribute that, and get an irreducible quadratic factor. So create a factor. For linear, this comes from a real 0, use synthetic division. A quadratic for a complex pair. So 2 complex numbers give you 2 factors. You distribute to get rid of the complex. That's why we practice that. And then we have to do long division because synthetic division will not handle that. After that, we try to factor the rest, or you repeat this. Find another 0, create another factor or pair of factors, which gives you an irreducible quadratic, and divide again, or synthetic division. So that's the whole thought process. Also, on this first example, we're going to sort of ignore that you can factor that, but in real practices, you would not do what I'm doing. You would absolutely group this, factor by grouping, and you'd be done. I'm just showing you on an easy example so that we get the idea of what to do with that, what to do with long division on something that, number 1, is a little easier. Number 2, students make a lot of mistakes on. Not because it's not easy, but because they don't know what to do when you distribute and you're missing a term. So I'm going to show you how to do that. It's a very important example for that. So let's get started. Number 1, we're going to find a 0, and if it has one, awesome. If it's linear, if it's a real 0, you create a linear factor. So if we would have got like, hey, it's -4, then we write x plus 4, and we have ourselves a linear factor. Here we have a complex solution, and so we have 2i. But we also know that complex solutions, or complex zeros, come in conjugate pairs, so we automatically get one for free. So 2i, we also know that -2i, which is the conjugate, 0 plus 2i and 0 minus 2i are conjugates. That's also a solution. Complex solutions always come in pairs like that. And so now what we're going to do is we're going to create some factors. We've done this before, but we're going to create x minus 2i equals 0 and x plus 2i equals 0. This is the way we go from solutions to factors. It's sort of using a zero product property to say, hey, listen, if these are zeros, well, then you can subtract 2i and get x minus 2i equals 0, but that would come from some polynomial factor being set equal to 0 and using the zero product property. So we basically go backwards and say that's a factor and that's a factor. What we do here is quite important. You see, with long division of polynomials or synthetic division, this doesn't work with complex numbers. And so we have to at least distribute to get rid of those complex numbers. What we're going to do is we're going to distribute this. This is pretty nice. This is already set up in conjugate form. It looks like a difference of squares, sort of. And so when we distribute, we get x squared. We would get plus 2ix and minus 2ix. Well, those are going to cancel. This is always the case when you're multiplying complex conjugate factors like this. And then we're going to get minus 4i squared. Remembering what I squared is. I squared is just -1. That's all it is. So x squared minus 4i squared is really x squared minus 4 times -1. Or x squared minus -4. Well, that's x squared plus 4. What I squared does is essentially just change the sign of that term. That's really all it does. This right now, if we think through it, we say, okay, hey, that's a 0. Complex conjugate pair says that also gives us a 0. Now that we have these two zeros, we can create some factors. No problem, we got it. Now they have complex numbers in it. Let's distribute to get ourselves an irreducible quadratic. That irreducible quadratic is a factor of this polynomial right there. It has to be because it came from the zeros. It's a must. So this is what we're going to factor out or divide out from our polynomial. I'm going to show you how to do that. Synthetic division will not do it. And this is why I taught you long division, is so that we could do this. And why I'm doing this is so that later on, when you get to some things that you have to do long division for, you're at least prepared a little bit. And so we're going to divide our original polynomial by the factor that we got from multiplying our complex linear factors, or they're sort of linear factors, factors that have linear factors that have complex numbers in there. We have to distribute those, and then we get a irreducible quadratic factor. Now let's go ahead and divide it. This works the same way as any other long division. It's just that you're not dividing by x. You're dividing by, in this case, x squared. So let's go ahead and divide. What we're going to do, same as always, is take our first term divided by our first term. I'm going to show you for a couple times. So x cubed divided by x squared. This is what we're doing. X cubed divided by x squared. The rest of this is just going to play along. And that gives you x to the first power. And then we're going to distribute. Remember that this is the way long division always works. You divide, and then you distribute, and then you subtract. So when we distribute, we get x to the third power plus 4x. That goes under here. You go, wait a minute, what are my x squareds? Well, you don't have any in this case. You see, you're missing that middle term because this is one of those sort of special irreducible quadratics that came from a 2i minus 2i rather than like a 3 minus 2i case, in which that's going to have a middle term. And I'm going to show you that one as well. So we have two examples here. So when that happens, I always give myself a little placeholder saying, hey, here's my x to the third power. That has to match. I don't have any x squared because there's no x to multiply, and then plus 4x. So I'm always matching up what my terms are. And the reason why I do that is because on the next step, we're about to subtract. So you've seen this before. You've seen me do this parentheses. This cues my brain into I'm subtracting each and every one of those terms. So I'm taking x cubed minus x cubed. Negative 4x squared minus 0x squared. And this is the reason why I put that 0x squared. If I don't do that, it's often that I'll subtract these and get 0, subtract these and get 0, and go, I have nothing left. What did I do wrong? By putting that there, I make sure that I'm actually performing a subtraction concept, and I basically bring down that term. But if I don't do that, most of the time I forget it. So negative 4x squared minus 0 is negative 4x squared. 4x minus 4x is 0. Minus 16. So I'm going to put 0x there just to keep my term. I don't necessarily need it, but I put it there just to keep that, like a place value holder. And so then I'm going to take my first term and divide it by my first term again. So negative 4x squared divided by x squared. We're going to get negative 4. And so we're going to write minus 4. And that basically completes our division. We're just going to go through the distribution to make certain that what we do gives us a 0 remainder. If it does, then we've done this right. If it doesn't, we've made a mistake on our division because we already know that that has to be a 0 and that has to be a 0. These have to be factors, and if we've distributed correctly, then that is an irreducible quadratic factor of what we've been given. So it has to work. It has to give us a 0. So let's distribute, make sure that happens. Negative 4 times x squared is negative 4x squared. I don't have any x's, so there's still a 0x. And then negative 4 times 4 is minus 16. And this looks perfect because when we subtract, we're going to get negative 4x squared minus negative 4x squared. That's 0. 0x minus 0x is 0. I made a mistake. I don't know why that's 14. Weird. Negative 16 minus negative 16 is also 0. Well, that gives us a lot of confidence that what we did is perfect division, and that's fantastic. So here's what this means for us. What this means for us is that we have now found a quadratic factor, we've divided out, and we're left with our quotient of x minus 4. That's a linear factor. That means that we can't really go any further, and this says that our polynomial, if you needed to write this in factored form, you could write it a number of ways. So the first way that you could write this as factors with complex. This would take our degree 3 and say you now have 3 factors. You have x minus 4, that's included in a real solution. You have x minus 2i, we had that here. X plus 2i, you have that here. This is factored over the complex number system. If you have to show factored over the real number system, then you just say, well, you know what, we've done that. When we go ahead and distribute these complex factors, we get an irreducible quadratic. But that irreducible quadratic is only irreducible over the real number system. And that would show factorization over the real number system. That's good. And lastly, if you need to show all of your zeros, so if you need to show all your solutions, we already really had one. We got another one for free. And lastly, we know that if we set x minus 4 equal to 0, we can use a zero product property again. So x minus 4 would equal 0, x would equal 4. That'd be a multiplicity 1, that'd be a cross that fits our paradigm, that's an odd polynomial, odd power function. It has to cross the x-axis at least once, and it does right there. That's our only x-intercept. It is a cross. Look at the multiplicity 1. That's got to make sense to you. And then we have 2 complex solutions. This probably gives us some sort of turning points that don't interact with our x-axis. So that's what I want you to know about this. So the main things here are, if you're given complex, you automatically have another. Multiply those factors first to give yourself an irreducible quadratic. Then divide it out and deal with what you have here. Sometimes you'll have to continue to factor that. If you don't, you're good. Like here, this is fine. We had basically 2 factors wrapped up here. Here's our third factor. That's a degree 3. Degree 3 means 3 factors if you factor over the complex. Degree 3 means 3 solutions all the time if you include complex solutions and sometimes multiplicity. So let's go on to the next example. Here, this next one, this g of x, this is clearly not factorable. We don't have a GCF in there. This is not going to work with factoring by grouping. So we're really left to, we need to know a factor in order, a 0 in order to create a factor in order to divide this. So the 0 that we have either comes from like rational zeros theorem. This is the most often case, like where you know nothing about it and you start plugging in numbers. And those numbers come from that list that we learned about. You go, okay, well, that would work. And then I divide out a linear factor. By synthetic division, it's actually fairly quick. That's the last 2 examples we do today in this video. But here they've given us a 0, 3 minus 2i. And so we're going to go through the same process. Just please be aware, with one complex solution, you really can't do much as far as factoring that. You can't. because you can't do long division of polynomials with a complex number. It doesn't work. And so what we're going to do is we're going to use the idea of if you give me one complex zero, I automatically know another one. They always come in pairs. By the quadratic formula, they have to. They always come in pairs. And so we're going to take those complex conjugate pairs, build a pair of factors. So find a zero, we got one. Create a factor. Hey, a quadratic comes from a complex pair. Let's get a pair. Let's distribute them. Let's get a irreducible quadratic, and let's factor that out. So we're going to start with that. So we look at it, we go, okay, I want to find all the zeros of that polynomial. In your head right now, you should be thinking there's going to be how many? There's going to be 4 of them. That's a degree 4. There should be 4 zeros and 4 factors over the complex number system. Can I factor it? No, I can't. Do I have a zero? Can I find a zero? Yep, I have one. That's 3 minus 2i. And when that's complex, you have to find a pair. If it's real, you're good. If it's a real number, like I said over here, it was going to be 4. So if it's a real number, well then x minus 4 is your factor, and do synthetic division or long division, and you're good. But with a complex, you need a pair of them. So 3 minus 2i, oh yeah, the pair would be 3 plus 2i. And we're going to go through the process of creating those factors. I showed you this in another video where when you have a complex solution, really take the time. Don't just go straight to the factor. Write these as equal to 0 and then group your first 2 terms to create this sort of 2-term times 2-term multiplication. So we're going to subtract 3 and add 2i. Subtract 3 and subtract 2i. And these right here become our complex factors. But I hope you remember that this is really difficult to distribute if you just take 3 terms times 3 terms. That gets really nasty. And so what I taught you in another video was just group these first 2 and group these first 2. On a complex conjugate pair, your real part is the same. The 3 and the 3, it's always the same. And so when we subtract that, you're going to get the same exact expression on both of your complex conjugate factors. Both of them are going to have, in this case, an x minus 3. Group that. Group that. And then these become your factors. And we treat them like they're 1, 2 terms, 1, 2 terms. So when we distribute, it's much nicer. It creates this conjugate factor for us where the middle terms cancel, where we just have x minus 3 squared. It's a lot easier. We've studied that in another video, so I'm not going to go into it fully right now. But this is the way that we're going to go ahead and distribute because it's so much nicer than treating this as 3 terms times 3 terms. Okay, so we had a complex 0, we got another one for free. We created complex factors, we grouped the first 2 terms, and now we have this sort of conjugate, not really sort of, I guess it is sort of because this is not really one term, but a conjugate look to our factors. When we distribute this, we're going to distribute x minus 3 times x minus 3. We get x minus 3 squared. If you were to distribute, you get minus and plus the same exact thing. That's going to cancel. That's going to give you 0. So then we're going to distribute 2i times negative 2i. That's minus 4i squared. We talked earlier about a couple things and refresh your memory. Number 1, when you are doing this and multiplying complex conjugate factors like you're doing here, you will always get a minus, you'll always get an i squared, which will change this to a plus every single time. Also, why we're doing this again is that you cannot divide this on a polynomial over the real number system. It doesn't work. So we basically have to have a pair. We have to have these 2 factors. We have to distribute, and we have to simplify this into an irreducible quadratic. So when we do that, this gives us x squared minus 6x plus 9 minus 4i squared. Just remember that 4i squared is really plus 4. That I squared is negative 1. And so subtracting 4 times negative 1, well, that's really adding 4. So here's what we know about that. We know that this right here is an irreducible quadratic, but we also know, because it came from two things that we were assured were solutions to this polynomial, that the factors we created another factor for that polynomial. In other words, this has to divide that, for sure. So we're going to show that. And so we're going to do long division because synthetic division is certainly not going to take care of that for you. Synthetic division works only for linear factors and only when your x has a coefficient of 1. So let's go ahead and let's divide. We've already got this set up appropriately where every single power less than our degree is represented, including a constant. If there was no constant, you could factor that because everything would have an x in it. That of GCF, you could at least factor that. We have our irreducible quadratic. Yes, you must have that to do long division of polynomials. Is an irreducible quadratic. Linear factors with complex numbers do not work. And so now we're going to divide. Again, it's just your first term divided by your first term. And here, this is actually a little bit easier than this one because everything matches up term for term. So we're going to see that. So when we start dividing, we're going to take x to the fourth divided by x squared. X to the fourth over x squared gives us x squared. So when we multiply, we're going to distribute. Your first term should always be the same when you distribute. If not, you've chosen the wrong thing. X squared times negative 6x is minus 6x to the third, and then plus 13x squared. We always put parentheses, we always subtract, we always remember that I'm subtracting term by term. X to the fourth minus x to the fourth is 0, that's what we need to happen. Negative 9x cubed minus a negative, so that's plus 6x to the third is negative 3x to the third. 21x squared minus 13x squared, that's going to give us 8x squared. And we're going to bring down 21x and do the same thing again. So we take our first term, negative 3x to the third, divided by x squared. Well, that's going to give us negative 3x. So we write minus 3x. And we're going to distribute again. So x squared or negative 3x times x squared is negative 3x squared. That looks good. Negative 3x cubed, I meant to say. Then negative 3x times negative 6x is positive 18x squared. Negative 3x times positive 13, well, that looks like negative 39x. We're going to have to be really careful on signs here. So negative 3x cubed minus negative 3x cubed, that's 0, that's perfect. 8x squared minus 18x squared, that's negative 10x squared. 21x minus negative 39x, so that's adding 39x. That's going to give us 60x. And our last step. So we're going to take a look at this, and we're going to divide our first term by our first term again. Notice how the long division of polynomials is really just based on the first term, and everything else just gets distributed and plays along. That's how it works. It looks really confusing the first time you see it. You go, what am I supposed to do with all this? Just focus on your first terms, you're going to be fine. So negative 10x squared divided by x squared gives you negative 10. We're going to put minus 10. We're going to distribute one last time and just make sure that our remainder is 0. Negative 10 times x squared is negative 10x squared. Negative 10 times negative 6x is plus 60x. That's looking good. Negative 10 times 13 is negative 130. And we can tell when we subtract something from itself, we get 0. And so that's perfect. That's exactly what we want. Now, what do you do from here? Well, what we've just done is we've reduced this polynomial, we've factored it into two quadratics. Now, we already know that one of them is irreducible. This is an irreducible quadratic. You cannot break that down anymore. But this one's not. This can be factored. So there's the first step in how we factor this polynomial. We have two quadratics. This one came from our linear factors that had complex numbers in it. So we're not going to be able to factor that in any other way. Factoring is unique to a polynomial. So you're done for this one. This one came from these two. Unless you want to break that down into linears that have complex, which you can do, we're just going to leave that. We basically use that quadratic to figure out what was left. Now, this one, you need to go a little bit further on that. So x squared minus 3x minus 10, that's factorable as x minus 5 and x plus 2. This would be completely factored over the real number system. So this is good to go as far as a real number system. If you have a factor over the complex number system, well, then you would go back and you'd say, all right, there's x minus 5, there's x plus 2, and we actually already have those factors. X minus 3 minus 2i, and x minus 3 plus 2i. That came right from here. This would be completely factored over the complex number system. So you have 1, 2, 3, 4 factors. That's a degree 4 that matches up. How many solutions do we have? Well, using the zero product property and going kind of quick on it, we'd have x equals 5 and negative 2 and x equals 3 minus 2i. And 3 plus 2i. We already knew this one. We got this one for free, and then we just figured out these two from that quadratic. That's the process of going through and solving these. So we have a degree 4, we have 4 complex factors. We have a degree 4, we have 4 complex solutions. We have a degree 4 over the real number system. You have an irreducible quadratic because that gave you complex solutions. I hope that makes sense. I hope you're seeing the interplay between this stuff. The last thing I need to mention to you about this before we go any further, what if that was not factorable? Most of the time it's gonna be because you're working out of a textbook or something. But what if that's not factorable? Then what you would do is you would use the quadratic formula. So you do quadratic formula, it will give you 2 solutions. Whether they're real or complex, I can't guarantee you. It could very well be the case that you have a degree 4 with all complex solutions. That's possible. What if you have a degree 4? It could look like this, where it doesn't intersect the x-axis at all. You're going to have 4 complex solutions. Here, we know we intersect the x-axis, and it's a multiplicity 1, so we cross the x-axis at those 2 x values. We know that. It goes down, and it comes back up, and it probably does something, some weird little loop that doesn't interact with the x-axis. We get a picture of that because we know about graphing. That's why I taught you that stuff. So I guess long story short, your degree has to match up with your complex solutions, not necessarily your real. That's the maximum number of real solutions you could have. It's the exact number if you include complex. That's the maximum number of factors you can have for real numbers. It's the exact number of factors if you have complex. So here we have 1, 2, 3 factors, but one of them is irreducible quadratic. Here we have 1, 2, 3, 4. Again, that could be, if you cannot factor it, that could be something you need to do with quadratic formula. It can look a little nasty when you start using the quadratic formula for that because if you have to write factors, because your factors could be x minus something that comes from a quadratic formula and x minus the other thing that comes from a quadratic formula like this. This just came out of nowhere, but if I had a quadratic that gave me this solution and that solution, notice x minus and x plus and x minus, 1 plus square root of 3 over 2, that does not come from this, I'm just making this up. Then you write x minus that and x minus that, but that looks a little bit nastier, doesn't it? It's still a real number. I mean, it doesn't have an I in it, it's still a real number. So it's factored over reals, but that's what we would get out of that. So I hope that makes sense. The next 2 examples we're going to talk about, don't forget to factor, like what we should have done on that example. So I'll be right back with that. All right, let's keep on going. So one thing is that a lot of times when students are in a section, they focus on the technique of the section, and it seems like everything they've learned before just goes out of their mind. The way that I teach, I always try to do what's called spiral. I always try to look back at stuff you've learned, incorporate in what you're learning, and not so as to not forget about it. Because the things you learn first tend to be easier. And if you can use them, why not use them? And this is two examples just to reiterate that factoring is very useful. And as far as easiness, it trumps what we've been doing because using the rational zeros theorem for something like that is just way overkill when you can factor it very easily. Same thing for that. So we've learned some techniques, just don't forget about them. So when you're going through this, I really don't care what they tell you to do. If it says, yeah, use rational zeros theorem, but you can factor it, why are we using rational zeros theorem? There's other ways to practice that. So let's factor when we can factor. So if we take x to the fourth minus 1, and you're tasked with finding all of the zeros of this, well, we could use rational zeros theorem to give us a hint, but notice how we're not given any zeros right off the bat. We're not given a complex like we were in the previous two examples. Then we could build another pair, two pairs of factors, distribute for a irreducible quadratic, and do long division. That's great. We're not given that here, so we're starting from scratch. We could start with rational zeros theorem, but why? Why when we could factor? So if we set this equal to 0, and that's how we find all solutions ever, set it equal to 0, well, then that's a power 4, but it's modeled on a square of a square, x squared squared. So you probably have seen the use a substitution. I know we've done it in this series where u equals x squared, and you do that. You can just straight up think, hey, you know what? That's a difference of squares with x squared minus 1 and x squared plus 1. And that's a true story. X squared minus 1, x squared plus 1, that's x to the fourth plus and minus x squared is 0 minus 1. That looks like a difference of squares. Why not factor it like a difference of squares? If you want to see it a little better, you can think of this as x squared squared minus 1 equals 0. That's x squared minus 1 and x squared plus 1. Okay, well, how about that? Well, let's keep on factoring. Can you factor x squared minus 1? No, that's an irreducible quadratic. Can you factor x squared plus 1? No, sorry. X squared minus 1? Yes, that's not irreducible. That's a difference of squares legitimately. X minus 1 and x plus 1. And then you'd still have x squared plus 1 equals 0. Now, here's what I'm going to tell you. This is completely factored over the real number system. You have a linear, which is going to give you a real solution. And it's going to be a crossing because we have a multiplicity 1. We have another real solution, a linear factor gives us a real solution. Multiplicity 1 says we have another crossing. This right here, you do not say it has multiplicity because multiplicity comes from the power of the factor, not the power of the term. So that x squared plus 1, it's not factorable. The quadratic formula would give us an I in there. This is an irreducible quadratic. So this is not giving us real zeros. This is not giving us x-intercepts. But we still need to know how to find complex solutions. So how do we do that? Well, we start with the easy factors. We go, all right. How we find zeros is by using the zero product property. We have these factors set equal to 0. We have two linears and an irreducible quadratic. Where we go from there is using the zero product property to say, well, yeah, x minus 1 equals 0 and x plus 1 equals 0. And sure enough, x squared minus 1 plus 1 would also equal 0. Now this is really nice. X equals 1 and x equals negative 1. What you do with irreducible quadratics is one of two things. Listen carefully. How you solve these is factor if you can, find a factor if you can, with a real zero typically, or like I used earlier, a complex zero where you find a pair, create irreducible quadratic, and divide. So find a factor. Okay, great. Factor it. Okay, great. Factor as much as you can over the real number system. It should be linears and irreducible quadratics. Set your linears equal to 0 by the zero product property, but also set your irreducible quadratics equal to 0. These are very easy to solve. These are both crossings, multiplicity 1. They're real x-intercepts. The graph is going to cross the x-intercept twice. For irreducible quadratics, this falls into one of two cases. Number one, something like this, where you can solve for your x squared and simply take a square root. Yes, you will get i's. You know what? For all your irreducible quadratics, you get i's. So we're going to subtract 1 x squared equals negative 1. When we take a square root, oh, don't forget, you gotta have a plus and minus. Don't forget that. We get x equals plus or minus the square root of negative 1. Well, wait a minute. The square root of negative 1, by definition, is exactly what I is. And what I is an imaginary number. So we get plus or minus I. That gives us two solutions. We get I and negative I. That's case 1. If you have x squared plus some number, then you solve it just like I showed you. Set it, solve it for your x squared, take a square root plus and minus, and you get a complex number out of it. If it's x squared minus a number, you better factor that. Even if it's like x squared minus 5, remember you can do x minus square root of 5 and x plus square root of 5. So x squared plus a number, yes, complex. X squared minus a number, no, not complex, real numbers. That's factored. You'd have two solutions. You'd have square root of 5 and negative square root of 5. Now, what if this wasn't x squared plus a number, but something like x squared minus 6x plus 13? What then? Well, then you would do the quadratic formula, and it will show up your zeros for you. And you can write them as factors if you need to. So we're going to do both of those things. Right now, we've found for the degree 4 are 1, 2, 3, 4 solutions. This is all we're asking for, is those 4 solutions. Next, if you have to write this as completely factored over the real number system, this is it. This is factored over the reals. If you have it factored over the complex, then you just simply go back, and from here you create your factors. We already know these two, x minus 1 and x plus 1. From these two factors, you can get x minus I. This looks really familiar because we've done it. X plus I. And those would create 2 additional factors for you that include complex numbers. This would be completely factored over the complex number system. Degree 4, 4 factors, but some of them are complex. So I hope that makes sense. The biggest thing here is don't ignore factoring. If you can use it, it's way quicker. Let's look at the next one. So x to the 4th plus 13x squared plus 36. If we remember, I'm going to use this with a substitution so we can sort of spiral that into. For things that have a power here that's twice the power here, you can do a substitution. So we're going to call u equal to x squared. And what that means is that x to the 4th would become x squared squared, or u squared. Remember, x to the 4th is x squared squared plus 13x squared. So we can call this x squared and that x squared this u, some dummy variable. So u squared plus 13u plus 36. I'm going to speak a little bit about this when we're done. We're going to come back and say, well, what if you couldn't factor that? Try again, because almost always they're factorable. But what if you really can't? We'll talk about that. This is factorable. So g of x, really it's g of u at this point, would become u plus 9 and u plus 4. That's u squared plus 4u plus 9u, that's plus 13u plus 36. That's the way the substitution works. If you set this equal to 0, and we're solving this now, so u plus 9 would equal 0, and u plus 4 would equal 0. Okay, I suppose that's fine. U would equal negative 9, and u would equal negative 4. That also looks okay. Well, but then we have to go back to our x's. You see, we start in terms of x's, and we got to use our breadcrumbs to get back to our x's. So if u equals negative 9, we knew that u equaled x squared. Therefore, x squared equals negative 9, x squared equals negative 4, and we run into exactly this same situation where we can take a square root with a plus minus, and we get x equals plus or minus 3i, square root of negative 9 is 3i, and x equals plus or minus 2i, square root of negative 4 is 2i, and this gives us our 4 solutions. Degree 4, 4 solutions. If you need this to be factored over the real number system, it's a little more difficult because we did a substitution. There's a different way you could go about it. If you just recognized that this is a 3-term polynomial and you can factor it, then you'd get down to here and you'd go right back and say, well, wait a minute, that's really x squared and that's really x squared, and this would be an irreducible quadratic in each of those cases. So you could stop right here and say that is factored over the real number system, and you'd be correct. That's 2 irreducible quadratics is the case I just spoke about, where degree 4 can certainly give you 2 irreducible quadratics over the real number system. These cannot be factored anymore. You can't factor x squared plus 9. You can't factor x squared plus 4. If you wanted to go further and do complex from here, that'd be fine. You do x squared plus 9 equals 0, and x squared plus 4 equals 0. And hopefully you can see that's the same case as this. You'd subtract 9, subtract 4, and end up right here. You get the same exact solutions. So this would be factored over the real number system. These are all of our solutions. There's 4 of them for degree 4. If you needed to give these factors as complex factors, well, then we can create a factor from each of these solutions. So we have x minus 3i and x plus 3i. Respectively, this would be minus because you'd subtract 3i, and plus because you'd add 3i. That would give us 2 factors, x minus 2i and x plus 2i. That's 4 factors, degree 4. 4 solutions, degree 4. 2 factors over the reals because those are irreducible over the real number system. Now, I mentioned to you, what if this was not factorable like this? Then what you would do, it would get a little more complicated. What you'd do is you would, from here, you'd solve for u with the quadratic formula. You would take that and you would simplify it down. Now this of course would give us some really easy numbers, but if it didn't, what would happen eventually is you would get u equal to some sort of an expression that looks like this. And then you'd say, okay, as soon as I simplified this all the way, as much as I could, then we'd do our substitution back. And you'd say, all right, x squared would now equal this expression, which I'm just modeling the form for you, and then you take a square root. And you take a square root with a plus and minus. And you can see that this would get a little bit crazy. You get x plus or minus some big square root that also has a plus and minus in it. It would look like that. And so do you have 4 solutions here? Yes, you do. You take positive square root of number plus square root of a number, then negative square root of number minus, said that wrong in the second one. You take positive square root of number plus square root of a number, you take negative square root of number plus square root of a number, then you'd say positive number minus square root of a number, and negative square root number minus square root of a number. You'd have 4 iterations here. Some of those could be complex numbers. So you'd have to really think about that. It gets really nasty. I don't foresee that you would see that many times, but this is what you would do if you get there. I can't think of an example that would be put in like a textbook for you, but it could appear somewhere. So anyway, I hope that makes sense. If this is not factorable, which almost certainly is, then you do quadratic formula, and when you get to here, when you simplify this quadratic formula, then you say, oh yeah, u is x squared. How do you get rid of x squared? You take a square root with a plus and minus, and you get positive for one solution, positive negative for another, negative positive for one solution, negative negative for another, and you get 4 solutions. Where we get crazy is for your factors. So you write x minus each of those 4 really nasty looking solutions as factors. So I hope it makes sense. The next 2 examples, we're going to start from scratch. I'm just going to give you a polynomial that's not factorable. We're going to go through rational zeros through. We're going to factor out with synthetic division. We're eventually going to get down to things that we have to use a quadratic formula for or have some complex zeros. I'll see you in a minute. All right, we're gonna get to it. We got just two more examples and they look kind of crazy. We're gonna find all the solutions to these polynomial functions. We're gonna start with rational zeros theorem. We're gonna factor out by synthetic division and eventually, hopefully, factor down and get some complex solutions as well. So a couple things to understand is I'm going to be going as quick as I really can while explaining this well to you, because everything that we're going to be doing on here we've learned already. I'm just giving you two examples to wrap everything together. That way when you get there you go, oh yeah, okay, I know what to do now. I know how to put it together, put all the pieces together. So let's take a look at these. Number one, we have f of x equals x to the fourth, and that's in order, and that says that we have a degree 4 polynomial. How many solutions we should get is 4. Are they all going to be real? I don't know. Could they? Yes. The degree is the maximum number of real solutions you get. It's the exact number of solutions you would get if you talk about complex numbers as well. So we should get 4 solutions, because we're factoring for all solutions here. 4 solutions, 4 factors over the complex number system. How we start. Try to look for factoring. That's 5 terms, we're done. You're not going to be able to factor 5 terms unless you have a GCF, which we do not have here. We have a constant, which eliminates our ability to factor an x. We have a leading coefficient of 1, which says we're not going to have a greatest common factor that includes some sort of a constant. So we're done as far as that goes. The next thing we do is try to look for a 0. There's none given. We don't have a complex 0. They're not giving us a real 0 here. So we're going to have to go through and find a 0. The best way to approach that is to get a list of numbers that you can sort of guess and check. So we're going to do that. We're going to say, all right, how we develop this list, rational zeros theorem. It says we're going to take our last term, our constant, figure out the factors, first term, constant, our constant coefficient, leading coefficient, find all the factors, and then create a list of numbers that are potential zeros for our polynomial. So for 75, that's our p, we'd get 1 and 75. Not 2, that's not going to work, but 3 and 25. 4 is not going to work, but 5 and 15. 6 doesn't work, 7, no, 8, no, 9, no, 10, no, 11, no, 12, no, 13, no, 14, no, 15, yes, it's already on the board, we're done. That's how you go through and do it. As soon as you cross this sort of bridge and to get from one factor to one you already know, then you're done. This is all the factors 75. And we have to include the fact that they could be positive and negative. One thing we might consider doing is Descartes' rule of signs right now to determine what, if any, we can eliminate. So when we look at this, we have 0, 0, 0, 1 sign change. What that says is there will be one positive x-intercept. Well, that's interesting because that's a degree 4. It doesn't even have to have one, but we know for sure this is going to have one positive x-intercept. So maybe keep that in the back of our head. If we want to change the signs of our odds, so make that a minus and that a minus, then we'd have 1, 2, 3 sign changes. So there's either going to be 3 or 1 negative x-intercept. If you don't remember that, maybe go back and watch Descartes' rule of signs because I explained all of that in there. How to change your odd exponented terms, and then counter signs again, sign changes again. So 1 sign change, 2 sign changes, 3 sign changes, that's not a sign change. So it would be 3 sign changes gives you either 3 or 1 negative x-intercept. So keep that in the back of our head. Honestly, what that means though is that we have to keep both positive and negative because we're going to have one positive, we have at least one negative. So we're going to keep our positive and negative. As far as our first term goes, the coefficient there is 1, and the only factors of that are 1 and negative 1. Which means that our list of numbers, we take the p and divide by the q. And so every sort of permutation of that we can arrange. We're going to get we usually get some fractions out of this. But here's all the numbers we need to check. Positive, negative 1, 1 over 1, 3 over 3, 5 over 5, 15 over 1. Sorry, 1 over 1, 3 over 1, 5 over 1, 15 over 1, 25 over 1, 75 over 1, gives us this list. Same list as our p's. Here's what this represents. It represents all the possible rational zeros of that polynomial. It does not include complex. It does not include square roots. All it does is the rationals. It's a good starting spot. Now, if we go through all of this and exhaust it, we're really kind of out of luck as far as what we know in this class so far. So we check and we start with 1. Start with the easy ones. If you have fractions, leave those last. So start with 1. Okay, so 1 plus 2 plus 22, that's 25. Plus 50 is 75, minus 75 is 0. Oh, hey, look at that, we got lucky. We know that 1 is a 0 because when we evaluated it, when we plugged in 1, you got 0. What's that mean? If you plug in x equals 1, that means that your function height is 0. You're on the x-axis. That's exactly what we're looking for. We're looking for zeros. X-intercepts in this case. And so we know that 1 is an x-intercept, and that's going to create for us a factor. We always show what we've done. We always show what our x-intercept is. We always show our factor here, because this is what we're going to use to factor this. The first thing we're going to write is f of x equals x minus 1, something, 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 whatever that polynomial is, and then we're going to continue. So we know x minus 1 is a factor. Then you choose to either use long division with this dividing into this, or you choose to use synthetic division with positive 1, not negative 1. We're going to use synthetic division. So synthetic division, we use the coefficients of our polynomial. And we use the x-intercept, not the factor, the x-intercept. So we use positive 1. And how this algorithm works is you bring down your first coefficient, you multiply and you add. 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 And you should end with a remainder of 0 if you have authentically found an x-intercept. This has to happen. Here's what it means. We've reduced because we're factoring out. Remember, synthetic division only works with linears. Only. And so it's always reducing your degree by 1 for your polynomial that you're finding, your quotient. So we have reduced that power by 1. This is now going to be an x to the third. So we know our function, a couple things about it. We're going to have a factor of x minus 1. Notice how a lot of students put x plus 1 because they go, oh, I factored out the plus 1. It's right there, positive 1, x plus 1. No, this is why I have you do this. X equals 1 is your x-intercept, and that's what you use for synthetic division, but x minus 1 is your factor. This is why I taught you all those times to create your factor, so that you have that pattern in your head. The remaining part of the polynomial is factored as x to the third plus 3x squared plus 25x plus 75. So let's talk for a moment about this. This is going to be factorable, and we're going to factor by grouping in just a second. It's really quick. If it's not factorable by grouping, we talked about this in the rational zeros theorem video, where you'd go back to your list and you'd actually try 1 again. You'd say, hey, can I factor out a 1? Well, 1 plus 3 plus 20, no, that's not going to work. It's not going to give 0. Can I try negative 1? No. Can I try 3, negative 3? Well, maybe one of those will work. If it's not factorable, you go back to the same list and you just start going through it again until you find another factor, and you use synthetic division again on this polynomial. Same exact thing. Keep this factor, you get additional factors. Because this is factorable by grouping, we don't have to do that. So always check. That's why the last 2 examples were there. Always check factoring. It's much quicker. So when we look at 4 terms, in our head we should be thinking, let's factor by grouping if we can. Let's factor out an x squared. Let's factor out a 25. Hey, that's perfect. That means that we have another factor of x plus 3 and then x squared plus 25. We already know that we have a factor of x minus 1. This is factored over the real number system. This is completely factored. We have a linear, done, quadratic, but it's irreducible. You cannot factor x squared plus 25. Now, had it been x squared minus 25, yes, difference of squares. Had it been x squared minus 5, absolutely. That's still technically a difference of squares if you use the square root of 5. So yeah, you could. Or if this was x squared, let's say minus 6x minus 13. Yes, you could do that, quadratic formula. So with those quadratics, you run into one of two cases. Either you can factor it or do quadratic formula, or it's actually, that's all you can do. You can factor or do quadratic formula. You're either going to get real numbers or you're going to get complex numbers. So as soon as you see a quadratic here, try to factor it. I can't. All right, well then set it equal to 0 and do what the situation necessitates. In other words, setting this equal to 0, we get, by the zero product property, x minus 1 equals 0. And x plus 3 equals 0. And x squared plus 25 equals 0. And this gives us two real solutions. Oh, think about it. What are those? Are those crossings or are those bouncies? You should have that in your head. That's a multiplicity 1, multiplicity 1. Those are real solutions. Those are actual x-intercepts, and they have to cross and cross due to the multiplicity. Then we get this x squared plus 25. I'm going to move it up here. We talked about this in one of the last examples, that if you have x squared plus some number, it's not factorable, but you can isolate the power 2 and simply take a square root. If you have a middle term in here and you can't factor it, firstly, try to factor it again. But if you still can't factor it, then just use the quadratic formula. And the quadratic formula will work for any quadratic that you can't factor. Whether it gives you real numbers or not, it'll work. If you get some i's in there by a negative discriminant, a negative inside your square root, well, then you know that you have some complex numbers. If you don't, well, then you have real numbers, and you have 4 real solutions. Here, we are able to subtract 25, take a square root, and get x equals plus or minus 5i. And that gives us 2 additional solutions, 5i and negative 5i. If you were kind of curious about what I was saying before, if you had like x squared minus 6x minus 13, that's still not easily factorable. So you go, yeah, I don't know how to factor that. Use the quadratic formula. You're going to get real numbers here. What about x squared minus 6x plus 13? I still can't factor it. What would you do there? Quadratic formula again, but you're going to get imaginary numbers in that case. So that's the way that I would say go through and do that. So factor as much as you can. When you get to the quadratic, try to factor it, but if not, then quadratic formula will give you whatever you want. Now, if we do need to continue to show all the solutions, we've done it. We have a degree 4, we have 1, 2, 3, 4 solutions. If we need to show it as factored over the complex, we can do our x minus 1, x plus 3, x minus 5i, that's from this one, and x plus 5i. Remember, you can set this x equals 5i, subtract 5i, get a factor. X equals negative 5i, add 5i, and get another factor. This is completely factored over the complex. If you had to do the quadratic formula on this, like with a middle term or something in there, then your complex numbers can get a little bit more complicated, and this can be sort of nasty, but it's possible. Don't give up on it. So that's about all I want to say as far as that goes. Let's go on to our last example and go through the same process. Okay, so here we go. We have a degree 4. We should end with 4 solutions. We know no solutions right now, so we're going to find them. We're going to do the rational zeros theorem. We're going to take our p and we're going to look at this and go, hey, there's 2, 3, 1 sign change. That's 1 positive x-intercept. 1, 2, 3 sign changes. There's either 3 or 1 negative x-intercept, very much like that example. If you looked at it, here's 1 positive, here's 1 negative, and 2 imaginary solutions. So we're going to take a look at this as we go through and make sure that works. So we're always using Descartes' rule of signs sort of as a work saver and a work checker. And then we're going to take our factors of our constant, that's the p, and our leading coefficient, that's our q. So 18 has factors of 1 and 18, 2 and 9, 3 and 6. And because we have both positive and negative x-intercepts, we're going to have to include both positive and negative factors for that. If Descartes' rule of sign said, hey, you have no sign changes, you have no positives, then we'd just be looking at negatives and make it a lot easier. For Q, we have 1 and 3. Those are the only factors. And so our list of things to check is going to be 1, 2, 3, 6, 9, 18, 1/3, 2/3, 1, 2, 3, and 6. So we get a lot of repetitions here. So those are the whole numbers. When we do our fractions, we get 1/3. We get 2/3. We get 3/3, but that's 1. 6/3, but that's 2. 9/3, but that's 3. And 18/3, but that's 6. So we don't need to include those twice. That's just redundant. And then we're going to check. So we're going to check G of 1. We're going to plug in 1. There's no way that if I plug in 1, that's going to give me 0. We'd try -1, but that's not going to work. We'd try 2. 2's not going to work. We'd try -2. Actually, -2 is going to work. If we evaluate G of -2, it gives us 0. I've done this ahead of time to save time, so I'm not going to sit here and plug in a calculator, but I actually tried 1 and -1 and 2 and then -2, and I finally got to one that worked. So G of -2 gives me 0. Now, what does that say? What that says to us is that x equals -2 is an x-intercept. Awesome. We don't know yet if it's a bounce or a cross, but we know it's an x-intercept. That also means that x plus 2 is a factor, so that's what we're going to factor out. So how do we do that? How do we factor that out? If you have a linear factor, man, I'm really going to suggest using synthetic division. So we're going to take our polynomial with our coefficients and our x-intercept. It's got to be the x-intercept, not +2, -2. And we follow our synthetic division algorithm. We bring down our first coefficient, we multiply and we add, we multiply and we add, we multiply, let's see, and we add, we multiply, and we add together. Well, that looks pretty good. What that means for us is that we know one factor. We know that we have a factor over the reals of x plus 2. That's why we wrote that right there. We also know that synthetic division reduces the degree of our polynomial into by 1 into a degree of this inside factor of the polynomial. So 3x³ minus x squared plus 27x minus 9. That again is factorable. That's a 4-term polynomial. This is something we should check for grouping every single time. Now, if it wasn't factorable by grouping, then we'd go back to our list. You would not try 1, -1, or 2 again. You try -2 again just to make sure it doesn't work, and then you go through your list. The next one we'd find would be 1/3. So it would take us a long time to get there, which, thank goodness, this is factorable by grouping. So factoring out x squared, you get 3x minus 1. And factoring out 9, you get 3x minus 1. And this is perfect. This is what we want to see for factoring by grouping. We have 3x minus 1, and then we have an x squared plus 9. If we bring down that factor of x plus 2, this is completely factored over the real number system. But that's not what the question's asking. The question's asking for all of your zeros. And so because this is completely factored over the real number system, we're able to set this equal to 0. And by the zero product property, say x plus 2 would equal 0, and 3x minus 1 would equal 0, and x squared plus 9 would also equal 0. Even though it's a quadratic, that's fine. You can't factor that anymore. You could try. You would try. If it was x squared minus 9, you're good to go. You just use difference of squares. Or x squared minus 2, even minus 2, x plus 2 and x minus square root of 2 and x plus square root of 2. That's fine. Or if it was, yeah, pretty much that's it. If it's factorable, you could do that. It had 3 terms and you factor it. You could do that. But without that, you set all these factors equal to 0. So x plus 2 equals 0. That's x equals -2. And x equals +1/3. We add 1 divided by 3. That'd be way over there. Good thing we didn't have to find that one. And then x squared plus 9. For the last time, there's a couple cases here. If you have something like this where you can isolate the power 2, do it, take a square root, you just get a very simple imaginary number. If not, if you can't factor it, no matter what, use the quadratic formula. It will give you all the solutions because you can factor this into linears and irreducible quadratics. So linears, very easy. Irreducible quadratics, quadratic formula. It will still give you complex numbers, no problem. So we're going to subtract 9. Take a square root with a plus and minus, and get positive or negative 3i. That's x equals 3i and x equals negative 3i. Those are the 4 solutions that we have. Hey, look at that. There's 2 reals. We know we had to have that. There was 1 sign change here. That's 1 positive. Here's our 1 positive. Right there, 1/3. We had, when we changed our signs of the odd powered terms, we had 1, 2, 3 sign changes. That's 3 or 1 negative x-intercepts. Here's our 1 negative x-intercept. So there's 2 x-intercepts, 1 on the positive, 1 on the negative, both of which are crosses because of our multiplicity. And then there's 2 complex solutions that don't give us x-intercepts. 1, 2, 3, 4. If you had to show this factored over reals, this is it. That's an irreducible quadratic. If you had to show this factored over complex, we just write factors from every solution. There's 4 factors for degree 4. One last thing and then we're done. Please keep in mind that if you were to somehow know that 1/3 was a factor and you did synthetic division with 1/3, firstly, it's going to work. Secondly, this can look a little bit different. So I'm going to show that to you and then be done. If you were to factor this by taking that 1/3, and this is good practice because we rarely see it, this actually works with synthetic division of fractions. Just most people never get there. So it's never practiced. So when you run into it, you go, I don't know how to do it. Bring down your leading coefficient and multiply. 1/3 times 3 is 1. When you add that, you get 6. 1/3 times 6 is 2. When you add that, you get 27. 1/3 times 27 is 9. When you add that, you get 54. 1/3 of 54 is 18. And when you add that, you get 0. It actually does work. And it works fairly well, even though it's a fraction. They kind of scare you at first, but it's almost always the case, unless you have another fraction in there, that you end up getting these very simplifiable fractions when you start multiplying. So that's pretty nice. What I mean by this is that this factor can look a little different. This right here would be x minus 1/3 instead of 3x minus 1. Those need to be the same in your head. So x equals 1/3. If I multiply by 3 and subtract 1, I get 3x minus 1. If I just subtract 1/3, I get x minus 1/3. Those are the 2 ways that we can write that factor. So you'd see it this way, or like that, where you have a 3 that's been forcefully factored out of that. If you distribute, you'd get 3x minus 1. Which way is preferable? Probably that one because there's a fraction in it, but it doesn't really matter in terms of what we deal with. So I hope this video, I know it was a long one, I hope it makes sense, but it had to be long because it wraps up pretty much everything we've learned about polynomials in terms of solving for their zeros, whether the complex or the real. And now I feel like I've given you a very, very thorough explanation on what you do when you get into this, even to the point of, hey, what if you can't do that? What if this is not factorable, or solving for x squared using quadratic formula? And I've shown you how to do that as well. So I hope this made sense. We're going to switch gears now. We're going to start working on rational functions, how to graph those. It's going to be very cool. We're going to use multiplicity to do some pretty neat things. So I'll see you for that. I hope you guys are doing well.